Okay, the last class, do you still remember what we learned of the last class?
Yes, doctor.
Okay, what do you learn?
Similitude.
Yes, perfect. So what is a similitude? Another person. What is similitude? Pardon, Amma? Okay, what is similitude? This is just a revision. Similitude is a similar study that is used to predict the prototype from the model. Okay, simple. So, today's session, we're going to learn the normalized differential equation, DE, and internal flow. So, have you taken a subject we call a differential equation?
Yes, doctor.
Yes.
Okay,
Yes,
what
doctor.
subject is that? Is it a vector or just a differential equation?
Differential equation.
Oh, I
Sir,
see.
can you show the attendance again for a second?
Okay. Okay, today lecture, this is the today lecture. So, today lecture, we're going to cover the normalized differential equation. Okay. So what is a normalized differential equation? So any one of you know what is a normalized? What is the synonyms of normalized?
Is it first order differential equation?
Not really. That is a technical part. But this is the definition only. Normalized. What do you mean? What do we mean by normalized? Normalized mean it dimensionless. So the word normalized here basically represent dimensionless. So what are the example of dimensionless? Anyone? What's the example of dimensionless? Okay, it's okay. I will call one by one.
Doctor.
Fairuza Abdurrahman Ghazi, are you there? Fairuza Abdurrahman from section 1. Are you the Fairuza?
فيروزة مش موجود.
Fairuza not there?
الدكتور مطلع الليستة وعمل ايه؟ اوه طلعت؟
Okay. Fairuza, are you there?
عايزك تضيف اوكي اقول لك بتاعي.
Fairuza not coming? Okay, Fairuza not coming. Okay, Ibrahim Rajab from section 1. Are you there? Ibrahim Rajab from section 1.
Yes, doctor.
Okay, I would like to ask you, what kind, can you give example of any parameters that represent the dimensionless?
Like destination or
Destination? Are you in the geographic class before? Okay, do you join my class previously, Ibrahim?
Yes, join.
Okay,
Join.
what is a dimensionless? Basically, it's very simple. What is a dimensionless? Do you not understand from the previous class what is a dimensionless?
No unit.
Yes, dimensionless, no unit. Who said that?
Saya Nur Arisha Syahira.
From section?
Section 2.
Okay, Syahira.
Nur Arisha Syahira, ya.
Nur Arisha, okay. Nur Arisha Syahira. Okay, I give you 10 point. Okay.
Wow, thank you, Doctor.
Doctor, I have to give the answer.
Okay, you yourself previously, what's your name? Okay, when someone actively participate in my class, I will give you 10 points. This point will be used, will help you during your test or coursework, okay? Okay, Amar, you answer before this? Okay, so dimensionless mean it is unitless, no unit. For example, like Renault number. Okay, Renault number unitless, don't have any dimension. Rho VD over mu. Okay, so normalized mean dimensionless. This is the synonym of dimensionless. Okay, usually when using differential equation, okay, when we use differential equation, we are not saying the dimensionless, we are saying normalized. Normalize that differential equation to describe lamina and turbulent flow. Okay, what do you understand? What is the difference between lamina and turbulent? Okay, let me
Doctor, I
ask.
can answer.
Okay, your
For turbulent flow, the
Najmul
real
Islam.
number is greater than
okay. Wait,
renal.
one by one. Who said first? Abdallah.
Najmul Islam.
Okay, Najmul Islam section.
Section 1, Doctor.
Okay, Najmul. Okay, so what's the difference? If you get right, you get 10 points.
So, Doctor,
okay.
laminar flow is between parallel plates, where the shape is usually like a parabola. Due to friction with the surface, the top one gets a bit behind, in the middle part is straight parabola.
I think that is not accurate. I give you second chance. What is the difference between lamina and turbulent flow? In terms of flow.
Laminar has the flow of laminar varies, but turbulence has no. You can say in terms of flow, I can't really explain, but the flow is not constant in laminar, but in turbulence it's like very hazardous.
Okay, I think that is not accurate, but it's okay. I give you 5 points. Okay. So another one, would like to try. What is the difference between lamina and turbulent flow?
The renal number is greater than the renal critical number for turbulent.
Okay. Can you repeat that?
For the turbulent flow, the renal number is greater than the renal critical number.
Okay, that is in terms of Renault number. Okay, it's okay lah. Your name is
Iftikhar Rahman.
Iftikhar from
Doctor,
section.
Section 1.
Okay, Iftikhar. Wait, yeah. Your first name is Iftikhar Rahman Dishan. Okay, 10 point for you. Another one would like to try. What is the difference?
Yes, Ibrahim. Normalized teacher, that mean we can use calculation easily, like square.
Oh no, I mean, what is the difference between lamina and turbulent? Not normalized.
Can I try?
Okay, Aina from section.
I'm section 1. guess.
Okay. Aina Zafira. Okay.
Okay.
So what's the difference?
The difference is lamina is it's moving, flowing in a straight line, while turbulence they are
But the
kind of
turbulent?
destructive, like it moving.
Okay.
Turbulence
Yes.
like moving. Yeah.
Okay, that's a good answer because that is what I'm looking for. So, Aina, you got 10 points. Okay, so lamina here, lamina versus turbulent. Of course, the Renault number for turbulent is higher, while Renault number for lamina is lower. As well as the flow. The flow is smooth. Okay, smooth. This is okay, this is vice versa or chaotic flow, or it is a zigzag flow. Okay, so the difference between lamina and turbulent, the flow is smooth and the turbulent is chaotic, disorderly flow. Okay, give me example of lamina flow.
The flow in pipes.
Okay, the flow in pipe can be both lamina and turbulent, but can you give specific what's the application that really use lamina? Okay. Example.
Doctor.
Doctor?
Heating, cooling system use laminar flow.
Okay, good. Cooling system.
Yeah.
Yup, Najmul.
Blood flow is laminar.
Yes, blood flow.
Honey flow also, doctor.
Yes. So, your name Najmul? Section?
Section 1, doctor.
Okay, you got 10 point lah, 15. Okay, another one who said before this?
Can I?
Abdurrahman Muhammad Abar, section 2.
Abdurrahman, section
2.
Section 2.
Abdurrahman Muhammad Amar.
Amar Abrak, is it?
Yes. Yeah.
Okay. So, okay, the blood in our vein is actually flowing in a laminar flow. What do you think happen when it is flow in a turbulent flow? What do you think of our body? What happen? Okay, when our
blood pressure is very high.
Okay.
Because the blood is flowing too fast.
It will damage the veins.
Yes, because every blood carry oxygenated blood carry oxygen that need to deliver oxygen smoothly, so it need to move in a laminar orderly manner. Okay, so that is a application of lamina and turbulent. You can see the fluid mechanic basically apply. This is the fundamental, but when we look at our body, for example, our heart pump the blood flow to our vein. Okay, this use the concept of lamina, right, and turbulent flow for other application. So let's we dive into the normalized differential equation. Okay, so in vector form, the continuity and naviesto equation we can express in terms of in this way. Okay, basically this is in terms of the vector form, but inside the vector form we have the differential equation. Okay, this, can you see this triangle upside down, basically we call as a delta. Okay, del represent the gradient. Okay, inside the del we have the differential equation. You can see this is a differential equation. So this differential equation, basically you can see here, this is continuity equation and this is Navier-Stokes equation. Alright, so this form is in the form of differential equation, but this form is not normalized. That means this form is not unitless. So we need to convert this form differential equation into dimensionless, that we call as a normalized. Okay, so from here, where the kinetic pressure Pk is defined to be, okay, this is used to simplify the Naviesto equation. Okay, this is the definition of kinetic pressure, where P plus rho GH. Okay, so from here you can see P and rho GH we can replace with kinetic pressure. So from here we replace into the Naviesto equation in terms of kinetic pressure. We form this equation. Okay, this is fixed. You can see rho dV over dt, rho dV over dt equal to negative del Pk, because this one has been replaced by Pk. Okay, you can see when I try to factorize this one negative. Okay. Okay, P. Sorry. This is factorizing, become positive. Okay. You can see this one similar with this one. So we can replace this term with Pk. That is why we form this Naviesto equation in terms of kinetic pressure. Okay, so far you guys understand, yeah? Okay, so based on this simplified form of Naviesto equation, let's start forming the normalized differential equation. So how to form? We need to form the characteristic quantity. So this is what we call a characteristic quantity, where the asterisk here are used to denote the dimensionless quantity. Okay, here you can see U asterisk, which is represent the dimensionless quantity, where U over V. This is B. This is in the direction of X. This is in the direction of Y. This is in the direction of Z. You can see W over V, and then this one X over L. Okay, this is the characteristic quantity. Okay, because it is unitless or no dimension. Same goes to the pressure. This is the characteristic pressure, which is P over rho V squared. When you try to expand the quantity and simplify the quantity, you will find out that the unit is unitless. Okay, same goes to here. Okay, you can see this is time over L over V. L over V represent the time, right? So time divided with time is unitless. Okay. So form the velocity vector V as the characteristic form. Okay, you can see here this is the V asterisk. V asterisk, we know that this is the vector form. When it is in a vector form, we need to express in terms of I, J, and K direction. So this is U, V, W represent the characteristic velocity in the different direction, which is U, V, and W, which is represent into the X, Y, and Z direction. So U asterisk, you can see here, we replace with U over V. V asterisk we replace with V over V. And W asterisk we replace with W over V. So upon the replacement of U, V, and W asterisk, we will form this final equation. Okay. So simply we can say that U, V, W, we combine we form the V, only V. Okay, the V is a vector form that represent the U, V, and W vector quantity. And this V, V, and V is the same. So we factorize, we become V over V. Basically, this is V like this. To differentiate between V and V here. Okay, so same goes to the del. You can see the symbol of del as the characteristic form. Okay, basically the definition of del, when you learn the vector or differential equation before, the del is basically I, J, and K. Inside I, J, and K, we have the divisions of X, Y, and Z. Okay, this is the asterisk. Definitely, this is also asterisk, asterisk, and asterisk. Okay, from here, okay, X, Y, and Z asterisk, we know that X asterisk is represent X over L. When you try to replace the X asterisk, you will form like this. Okay. This is X over L. So it will be like this. Okay, L will move here. Can you see it is the same thing here? Okay, so far every one of you understand until this part?
Yes, sir.
Okay, thank you very much for your response. Okay, same goes to the Y and Z. Okay, so from here we can say that, okay, all the term have the L. You can see L and L. So from here I try to factorize L. It will be like this. Okay. So L is actually L, and this term basically the del. Okay, L del. You can see the same with this one. Okay. So introducing the above, all this that we have factorized and expand into the Naviesto equation and continuity equation. Okay. So let's start with the Naviesto equation in terms of kinetic pressure. So this one, okay, in terms of kinetic pressure. So let's write it down. All right. So rho d, this is the total derivative. Okay, over dt equal to negative del pressure kinetic plus mu del squared v. This is the this is the Naviesto equation in terms of kinetic pressure. Okay. Okay, so this one, okay. This one supposed to be not there. Let's delete this one. Alright. So let's start with V. I think better I start like this, yeah. Okay, this is the rho dv over dt. I write it down, yeah, because it's difficult to write to see from here. Okay, this is the Naviesto in terms of kinetic pressure. All right. So from here, we need to replace one by one. Let's start with V. Okay, let's use this one. Maybe. Okay, let's start with V. Let's start with V because I want to replace this V. We know that V here, from the asterisk form, from the characteristic, Okay. Okay, you can see here. Okay, this is the final form. This V asterisk is equal to V over V like this. Okay, so in order to get V asterisk must multiply with V like this. Okay, so V is equal to V asterisk must multiply with V this one. Okay, and T, we start with T. So T, what is the T here? You can see T. Okay, in order to get this T here equal to, okay, T asterisk multiply with L, okay, over V. Okay, so T here is a T asterisk multiply with L over V. And then you can see here we have the del. Okay, the del. So from here, okay, the del. How to get del? Okay, where is the del? You can see this one, this del, and this is the final. So the del asterisk is equal to L del. So how to get the del? Of course, del asterisk divide with L. Okay, so del asterisk divide with L. And last we have the PK. This is P. Whatever K, whatever symbol here is okay. When this is K, the other also will be the K. So P. How to get the P? We look at here. Where is our P? Now we have the P. Can you see? Okay. How to get this P? When this is PK, this is K. So P K is actually PK asterisk multiply with rho V squared. Okay. So PK asterisk, okay, multiply with rho V squared. Okay, and then we have this one. You can see this one no need to expand. Okay, you can see this is del squared. So when this is the del squared, we can simply del asterisk squared over L squared. Okay, until this section, until this part, you guys understand how I try to derive? And
Yes, doctor.
Yes, sir.
okay, thank you. So from here, why don't you substitute back into this naviesto equation? Okay, substitute into naviesto equation. This is the naviesto equation. So substitute back. I try to substitute. Okay, rho. Let's say this is rho. And D. This is the differential, total differential. This is unitless. Okay, just replace with D asterisk. It doesn't affect anything. Okay, and then this is V. V replace with this V, which is V asterisk multiply with V this. Okay, over with D. D we can replace with asterisk. And time we replace with this one. Time asterisk multiply with L over V. Okay, equal to negative del. You can see del is here, which is del asterisk over with L, and PK. PK is here, which is P asterisk K rho v squared. And then plus mu del squared. Del squared is here. So replace with del asterisk squared over L squared. And then V, where is the V? This V, which is V asterisk V. Okay, so what next we need to do? We need to simplify. So how to simplify? Okay, we try to simplify this one. Rho, okay, this V will be, okay, where is it? Okay, this V will move upward. So V multiplied with V squared. So rho V squared over L. This is L. So this is D asterisk V asterisk over D asterisk T asterisk. Okay, I hope you understand, yeah, until this section. Equal to, you can see here, rho V squared, okay, rho V squared over L. You can see this is L. Alright, and then this is negative asterisk and PK asterisk. This is the rearrangement only. Okay, and then mu V. Okay, so this is mu plus mu V over L squared. So this is, sorry, this is actually V. Okay, this is V asterisk squared. This is V. Okay, so from here you can see the left and the right hand side we have the same term, rho V squared over L, rho V squared over L, and this is V squared over L. So why not all this term we divide with rho V squared over L. So I try to divide, this is cancel, this is cancel, and only this part. So I rewrite D V asterisk over D asterisk T asterisk equal to negative del asterisk PK asterisk plus, how to solve this one? Okay, solve manually, UV over L over with this one, rho V squared over L. Okay, make a bracket, asterisk squared V asterisk. So try to simplify this one, L. Okay, this is L squared. Now I miss this one, this is squared, right? You can see this is squared. Okay, now simplify, L cancel with this L. And then V cancel with this V. So now what do we have? We have here D asterisk V asterisk, write it down, over D asterisk T asterisk equal to del asterisk PK asterisk. So this one, okay, rho. Okay, so how to solve this one? So this is mu plus mu, okay,
over rho.
Over rho VL.
Let's say, okay, this is, we have the V, this is rho over rho V L. Okay, perfect. And then we have this one, squared V asterisk squared. Okay, so from here, what do you notice from this normalized equation? Can you see this term?
Yes.
This is what basically?
Reynolds number?
Yes, Reynolds number is equal to okay. Let me call
1 over Reynolds number.
Okay,
Yeah, reverse, doctor.
It's okay, it's okay. Let me call Nur Christina Azida. Are you there? Okay, no. Emir Zikran bin Badardin. Okay, no.
Yes, sir.
Your name is Emir.
Yeah.
Okay. So what is a Reynolds number?
I believe it's the rho VL over mu.
Rho VL over mu. Okay. So this is the upside down. How to form the proper Reynolds number?
1 over Reynolds number.
So from here we can make 1 over rho VL over mu. This mu we move to the bottom side. It become like this. So rho VL over mu is the same with this term. So can we just replace this with this term? So you got 1 over Reynolds number. And finally, the normalized differential equation become like this. Okay. Negative asterisk del pk asterisk plus 1 over Reynolds number del square asterisk v asterisk. Okay, this is the final form of normalized differential equation for continuity for the naviesto equation. So what can you
Doctor, what does asterisk mean?
Asterisk means it is dimensionless. Okay, I believe I stated here. You can see here, the asterisk are used to denote dimensionless quantity, no unit. Okay. So this is for Naviesto equation. We have one more, which is, remember we introduced to you before. We have two equations before, Naviesto equation and okay.
Continuity?
Yeah. So your name is Abdul Rahman.
Yes.
From section?
Section 2.
Okay, Abdul Rahman. Omar. Yeah.
Yeah.
Okay, 20 mark for you. Okay, so we have another one more, which is continuity equation. Continuity equation. Okay, before that, what is actually the continuity equation? How do we derive before this the continuity equation? From
the Reynolds transform theorem, RTT.
Okay, that is a method from where? From the conservations of?
Conservation of mass.
Yes, perfect. Conservation of mass. So your name is Roman. From section?
Section 8.
Section 8. Okay, Roman, you got 10 points. Okay. So continuity equation, basically the derivation from the conservation of mass. Okay. By using the methods of Reynolds transport theorem. And then we assume that the density of the flow is
the same.
Constant. So the continuity equation from this section is like this. The del dot v equal to 0. Okay, this is basically the continuity equation. Okay, del dot V equal to 0. This is the velocity. Okay, you can see our del. Where is our del? This is our del. Okay, the velocity in the X, Y, and Z direction. Okay, so we have the del. So the del here equal to, you can see the del here is equal to del asterisk over L, right? Del asterisk over L. And our V here is actually V asterisk multiply with V. Okay, so from this one, substitute back into the continuity equation. So del, which is, yeah, okay, this one, del asterisk over L dot with V, which is V asterisk V equal to 0. Okay, from here, V over L, del asterisk V asterisk equal to 0. So this term we move to the other side, and finally del asterisk and V asterisk equal to 0. That is the normalized differential equation for the continuity equation. Okay, so far every one of you understand? All of you?
Yes, doctor.
Okay. Sometimes in other textbook or in other part, okay, when we write the normalized differential equation, not necessary to put this asterisk. This is just a basic form for you to understand. Okay, for the expert, for those are expert in this normalized equation or mathematician, they already describe this in the normalized form. Okay, they normally make like this. That means this is simply the normalized differential equation, because this is just a basic part. Because to let you grasp the the understanding of the dimensionless form. Okay, so that is actually part. Okay, basically why you need to understand, why you need to know the normalized differential equation. Because why? Because we need to understand the what we call it. Okay, from here. Okay. Okay, from the Naviesto equation. Okay, can you see from here? Okay. This is the Naviesto equation. Okay, this one. This is the Naviesto equation in the form of kinetic pressure. So can you tell me something about this equation? Okay, I would like to ask Muhammad Lutfi Juliandri. Are you there? Okay, no. Calvin Aditya, are you coming? Calvin coming. Okay. Okay, Rohit Abdul Khair, are you there?
Yeah, doctor.
Okay, Rohit Abdul Khair, what can you tell me something about this Naviesto equation? What is the nature form? Can you tell me the nature form of this Naviesto equation? Something that it can fly, it can flow. What's the nature? Can you tell me something about this Naviesto? Okay, Najmul.
Yes. As far as I remember, with the it's related to incompressible fluid. Navier's stroke. That's what I remember. Like describes the flow of incompressible liquid.
Describe the flow
of incompressible liquid.
Okay. That's it.
The velocity flow
Okay.
and the density.
Okay. Yes, that is correct. Incompressible. Okay, but sometimes the Naviesto equation can also be used in compressible. Okay, it's not necessarily incompressible. Okay, anyone would like to try? What is actually the nature of this equation? What can you tell me about this equation? Would like to try, anyone? What is the nature? Okay. Okay, can you see it is hard, right, to describe the nature? Is it? Is it? Okay, you can see it is very, very hard to describe the nature of this Naviesto equation because this is in the form of not normalized.
It's not normalized. Not
This is
normalized.
not normalized. When we normalize the Naviesto equation, what's the final one? Can you see here? Okay, this is okay. Okay, this is after we normalize the Naviesto equation. Can you see? From this normalized Naviesto equation, can we see what we have here? We have the
Reynolds number.
Reynolds number. So from here, this equation tell us the nature of Naviesto equation involve Reynolds number. So Reynolds number apply for the lamina and turbulent. So it has the viscous effect. Can you see? When we try to form in a normalized differential equation, we can have a lot of information about this equation. Okay, now you understand.
Yes, doctor.
Yes, doctor.
Okay. Yes, that is what then we need to normalize because we need to understand what is the nature. Now we have the Reynolds number. Okay. If we have the Euler number, EU, what does it mean? It has the
Pressure significantly drop.
yes. Your name, Hani?
Yes, Hani.
Ahmad from section?
Section 1.
Hani Ahmad. Hani. Hani, is it? Hani
Yes,
Ahmad. Okay, you got 10 points. Thank you very much. So when it has the Euler number, definitely the pressure is significant. Okay, so we can tell the more information about this equation. Okay. So I believe that's all about the normalized differential equation to let us understand more information about that particular equation. Okay, let's we review a little bit about the internal flow. Okay, tomorrow we're going to understand the internal flow. Okay, so this is basically the internal flow. We will go in detail. Okay. So what is actually, do you understand about internal flow? Before we go into deep. Internal flow, previously I already explained to you. Internal flow, we have many category. One of them is
confined flow, doctor.
Okay, confined flow. We have the flow in the pipe, right? The flow in the parallel pipe. Okay, in the channel. So all these is the internal flow, the flow inside something. So when we study the internal flow, the viscosity is dominant. Okay, so for example, the internal flow in a circular pipe. Why the viscosity is important? Because we have the
laminar flow.
Okay, because we have the friction factor. Along the pipe, we have the friction, right? Remember, along the pipe, we have the friction. This is our circular pipe. Along the pipe, we have the roughness. This roughness will pull the water from moving. Thus, it will become non-uniform flow. This is due to the viscosity. Right? So the Reynolds number is important when we deal with viscosity. Okay. So Reynolds number is the ratio of initial force to the viscous force. That means the initial force is due to the density, the moving inertia. Okay, and then divide with the viscosity that hold from moving. So that is what we call a Reynolds number. Okay. So Reynolds number is important when dealing with the viscous effect. So I want you to understand. The viscous effect definitely Reynolds number. When we deal with the pressure drop, Euler number. When we deal with the high speed flow, it is anyone?
Mach number.
Yes. Perfect. Mach number. You again, section 8, yeah.
Section 2, Abdurrahman.
Section 2. Okay, you got 30 points. Okay, so when the ratio is large, that means Reynolds number. Where is it here? This is Reynolds number, which is rho VL or rho VD over mu. When the ratio is high, that means this value higher. Okay, the initial force. This term, this represent the inertial, inertial force that is due to the density or mass lah, right? This is due to the viscous. You can see dynamic viscosity, viscous force. Okay, the initial force is like the momentum, initial. Okay, the viscous is the holding. So when the initial force dominate due to the high ratio, it is true when there is a short sudden geometric change. Okay, what it means when you have the pipe, you have the short change. Okay, you can see it's a very short and then change, short and change. The moving of the water suddenly abrupt change in the direction. So this is will have the initial force will high. Okay, the viscous effects are important when the surface are large. Okay, why the viscous effect relies on the area? Why the viscous effects relies on the area?
Because of the viscosity streams. Viscosity is not linear.
Okay, what's the equation?
The pressure. The pressure.
Friction.
So what's the formula? Do you remember tau?
Tau is equal.
The gradient over the viscosity.
Yes, mu du over
dv.
Okay, dy. Okay. Okay. So you can see here the viscous effects. This is the viscous effect. Oh, sorry. This is the viscous effects. It relies on the surface area. Okay, you can see the area having this area having involve the distance L multiply with the L. Okay, you can see we have the distance. Okay. So this one, when we move here, will become tau dy equal to mu du over du. You can see this viscous effect relies on the distance, the y. Okay, when you have the surface area height, this is height, this is height, the viscous effect important, this is height as well. Okay, so thus the Reynolds number equal to rho VL over mu. Another one, another version of Reynolds number, everyone, you still remember?
Rho VD over mu.
Rho, okay.
VD over V
VD over
V.
Okay, it is not accurate. It is
VD over nu.
almost. Okay,
VD over nu.
VD over. So your name? If okay, it is perfect. V L or VD over nu, not V tau. The symbol like this, Shira. This is not V, this is nu. Okay. So if the car, your section?
Section 1, doctor.
Okay, section 1. Ikhtifar. Okay, you got 10.20 marks for you. Okay, so this new, this is the symbol is new, yeah. Basically, is the mu over density, the same thing. When you try to replace this one, mu with mu over rho, you will get the same thing. Okay. This one until last, this one is the last part. Okay, laminar flow. This is the basic one, yeah. When we need to decide whether the flow is laminar or turbulent, we see the Reynolds number. When Reynolds number for the pipe is less than 2000, when the flow inside the pipe, the Reynolds number less than 2000, it is definitely laminar. When it is the channel is this, yeah. The channel is this, the cross-sectional area. This is channel. This is the pipe. The pipe is circular. Okay. The Reynolds number is 1500. This is the lamina. Okay. At sufficient height Reynolds number, the turbulent will occur. Okay. That's it about today's lecture. Tomorrow we're going to cover the internal flow as well as laminar flow. I think that's all for today. Thank you very much for your time. For those unable to scan your attendance, please do so before we end our session.
Thank you, Doctor.
Thank you, Doctor.
When can we see our result?
Your result? What result?
The test.
Okay. I have marking completely section 1 and 2. Give me time to complete section 7 and 8. Only 30 students. After that,
I am from section 1 actually. So you finished marking?
No, I want to finish all and then I will submit everything.
Okay. Thank you, Doctor.
Yeah.
Sir.
Okay.
No.
Okay. Just give me time to complete only 30 students and then I will share all the results. Okay?
Okay.
Okay. So I think that's all for today. Thank you very much. Tomorrow we have another one more session. Okay, I hope you be on time. Okay. And then that's all for today. I end my session with Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam.